Hi, everyone. Hey, let's look and see what happens if there's already another group on benzene when you try and do an electrophilic aromatic substitution reaction. Okay, so we're in key concept, unit 1, part 3 still. This is a loaded key concepts, isn't it? Previous videos, we talked about these reactions and their mechanism. Okay, and then the preceding video should have been about limitations of Friedel-Crafts alkylation and Friedel-Crafts acylation reaction. The two most popular, most common type of reaction to do the benzene. So they're highlighted here down the bottom. Come on, pen, there we go. And these two in this box here. Okay, so a quick little review of the last video. He said, hey, Friedel-Crafts reactions are really popular because it's a good way of making bigger molecules, connecting more carbon atoms to the benzene ring to make a bigger molecule. And there's so much variety. Lots of different groups could be added. The key feature, though, is if you're doing alkylation, you got to have an alkyl group connected to a halide, chlorine, bromine, or iodide. And if you're doing acylation, you have to start with an acid chloride. But then the other part of the molecule can vary. Doesn't have to be a methyl, could be something else. This doesn't have to be a methyl group, could be something else too. Okay, then we said, hey, as good as those two reactions are, they're not perfect. Here's some problems. So we had, well, first one, just realize the names say alkylation, acylation, so you can't have vinyl halides or aerohalides. That doesn't work. Darn it, the alkylation reactions create carbocations, which can rearrange. Gotta watch out for those. And then these are the two we're going to talk about in this video. Actually, these three. The third limitation is that if you have a strongly deactivating group on benzene, Friedel-Crafts reactions shut down. Both alkylation and acylation reactions turn off. They don't work. The other 6 reactions work, though. It's just for Friedel-Crafts. And then we also said number 4, if you have an amine on the benzene ring, it shuts down the Friedel-Crafts alkylation and acylation as well. And then Friedel-Crafts alkylation had this problem, limitation number 5, of going and keep on going. It doesn't stop. It polyalkylates, more than one group adds on. So this video is going to give you some basis for understanding these 3 limitations. 1, why are some groups deactivating? 2, well, I don't know about 2. The amine is going to be a strong activating group. The answer, I guess, number 2, point 2 is that it's so activating, it reacts with the callus. And it shuts down Friedel-Crafts alkylation, Friedel-Crafts acylation, because the callus just got used up by the amine. And then finally, point number 3, polyalkylation. How come some groups activate the ring? More importantly for exams, which groups activate, which groups deactivate? Help me here. I know, I was there as a student too, and we would quiz each other, we'd try and figure this whole stuff out, but we got a good system. Over the years, collected a lot of tips, some shortcuts. Let me share those with you. Okay. First thing you have to realize is if there's already a group on benzene, it's going to say where the incoming group goes. So all the groups that already are on the benzene ring at the start of the reaction, they are directing groups. The little director saying, hey, new group, I'm going to tell you where to go. So they determine the placement of the new group. They also influence how fast the benzene ring will react. These directing groups, groups already on the benzene ring, affects the rate of reaction, how fast it goes, and where it goes, where the new group goes. Okay, one of the things you need to know about this rates of reaction is that that's going to determine our major products. So I'll show you that in a minute. If you have a mixture, 2 different molecules containing benzene, you put it in the same pot, same round bottom flask, same beaker, one of those benzene rings may react faster than the other benzene ring. And then the other one is going to determine the major product. The one that's faster wins and is going to use up most of the reagent and to make your major product. Okay, so we need to know, here's the bottom line, the nitty gritty. Which groups are going to be speeding up, which ones are going to slow down, and which ones are going to send things to different parts of the ring. Okay, time to start simplifying. Here we go. Let's tackle the second point. Where does the group go? Okay, so here's the situation. We start with group X, some group on benzene, and we're going to do a reaction, some reaction, and it's going to put a new group. Let's call it Y. This reaction is going to put Y on the ring. What are these reactions? It's one of these 8. So reaction, if I choose this reaction, it's going to put a bromine on, right? If I choose this reaction, it's going to put the sulfonic acid group on the ring. So the reagents say what goes on the ring. But the group already there says where and how fast. Okay, so where can it go? Well, turns out there's 2 possibilities of where the group goes. Some groups say, hey, new group, I want you to go ortho to B. Goes right next to me. Remember ortho, meta, and para? Yeah, they're coming back. It's not only useful for naming, it's also useful for understanding directing groups. So you got group X on the ring. It says, okay, new group, I want you to go next to me or across from me. That's one type of directing group. We call those OrthoPara Directing groups or OrthoPara Directors, OP for short. There's another set of groups, group X, that does what? It sends the incoming group meta. So where this group is located, it says, hey, new group, group Y, go sit at the table, the benzene hexagon table, meta to myself. And we call those meta directors. Yeah, that makes sense. Meta directing groups. Those are the 2 possibilities. Okay, for students who like memorizing, memorize them all. I have lists of OrthoPara directors and a list of meta directors. Go ahead and memorize them all. For the rest of us who like shortcuts, memorize the OrthoPara directors. It's a shorter and it's a nicer list. It has a pattern to it. Okay, so here are the OrthoPara directing groups. First of all, what do they have in common? Or why are they OrthoPara directing? Why do they send the incoming group ortho and para? Has to do with the fact that they like to supply electrons to the benzene ring. They donate their electrons to the benzene ring. And if you remember the mechanism, if you don't, go back and watch that video. In the mechanism, one of the 3 pi bonds of benzene jumps out of the ring and grabs onto the electrophile, right? The electrophiles are the plus charges. They're going to be groups adding to the ring, while the lone pair on the benzene ring, the pi bond, one of the pi bonds, makes a bond to the electrophile. So the OrthoPara directing groups are going to supply the benzene ring more electrons so it can jump out and grab the electrophile. Most of these OrthoPara directing groups are activating. They're going to speed up the reaction. But they don't do it equally. And we need to know that so we can make accurate predictions. Oh, how are they OrthoPara directing? How are they electron donating? Most of these groups have a lone pair of electrons on the atom attached to the ring. Okay, if you need to memorize just, well, the least amount of information you need, remember this. If you can look at a molecule, hey, here's a molecule. Here's the atom attached to the ring. Does it have a lone pair? Well, HONC, H-O-N-C, 1, 2, 3, 4, nitrogen likes 3 bonds. So this nitrogen, yeah, I see 3 lines to it, but is that a good Lewis dot structure? Does it have an octet? Nope. Well, it must, if this is a neutral molecule, stable neutral molecule, it must be, must have an octet. So yes, nitrogen must possess a lone pair, so it has 8 electrons. Whoa, it's an atom next to, attached to the ring, has a lone pair. That's going to make an OrthoPara directing group. Sweet. So that's the shortest shortcut. for identifying the OrthoPara Directing groups. There is an exception, this last one here. Okay, another way to memorize or be able to identify the OrthoPara Directing groups is to memorize this list. And they're ranked. So starting from the bottom, weakly deactivating, they slow down the ring. Weakly activating, they speed up the reaction of the benzene ring. Activating, speed it up even more. Strongly activating, speed it up a whole bunch. They're the winners of the race. Where's the rate of benzene? Right here. So if you just have pure benzene, we're doing a race, benzene is going to be faster than benzene with a halide. Aryl halides react slower than just pure benzene. If you put an alkyl group or another benzene ring, that's going to speed it up. These two molecules, toluene and what is that, biphenyl? You don't have to know that. These two molecules go faster than pure benzene. But if you have an amide, where the nitrogen and its lone pair are attached to benzene, or if you have an ether, oxygen with its lone pair attached to benzene, these go even faster than benzene with alkyl groups and benzene rings, and it goes faster than benzene, and it goes faster than aryl halides. And the way there's a race is if you have an amine, remember the amine could be primary, secondary, or tertiary. Not sure if we classify nitrogen, but just think of nitrogen with 1 carbon, nitrogen with 2 carbons, nitrogen with 3, doesn't matter. It's nitrogen, single bonded nitrogen, that's an amine. And no double bond O next door, because that's an amide. And an alcohol, they go faster than ethers, alcohols go faster than amides. Alcohols and amines are the fastest. They make the benzene ring very reactive, enough to react the fastest in Friedel-Crafts reactions, in the nitration reactions, right? Adding the nitro group and so forth. Okay, so this is the list to memorize. A few years ago, I had another student say, okay, the way I remember this list is no, I refuse, like no, no, carbons, halides. Okay, let's start at the bottom. That makes the most sense down here. Halides, yeah, if you put a halogen on the ring, that's the bottom of the list of the OrthoPara directors. If you have some carbons, and we're talking straight carbons, right? Because technically, if you have an ether, there's some carbons in the molecule, more carbons in the molecule. Okay, we're considering the atom directly attached to the ring. So an ether is when the O is attached to the benzene ring, an oxygen, and that oxygen has 2 carbons. That makes it an ether. So when we talk about the third category, or OrthoPara directors, and we say carbons, we're thinking about straight carbons, just alkanes, or maybe another benzene ring. And the benzene ring could have carbons on it or whatever. This could be a long chain, it could be branches, could be a ring of carbons, alkane carbons. Then it's the third category. No, that's just standing for nitrogen and oxygen. And so I know it's annoying that it shows up twice. What you have to remember is that the first no means, yeah, that doesn't work so much. Maybe something like that. The first no means kind of clean. There's a lot of H's. Doesn't work so much with this N. N is the amine, where you just have some more carbons on it, or you have hydrogen. The O over here means you have an alcohol, just an O with an H. The second NO stands for amide, where you have a C double bond O on that nitrogen, so that makes it an amide. Or your oxygen has some carbons on it to make it an ether. No, carbons, halides. No stands for amines, alcohols, this N and that O. This no stands for the amide and the ether. Carbons, alkyl groups, another benzene ring, halides. You know the halides, fluorine, bromine, iodide. And you get a periodic table on the exam. So next to last column, halides. There you go. And in this order. No, carbons, halides, so you can predict the rates. Amines, alcohols on benzene, fastest. Halides on benzene, slowest among the OrthoPara directing groups. So bottom line is, these are the groups you have to memorize so you can identify them. If they're on benzene, the product of the reaction with these molecules, the new group has to go ortho or para to these groups. We'll do some examples in a minute. And we got the speeds. Okay, what about the meta directors, the other possible group? It's whatever's not on this list. Yay! So memorize this list. If it's not on this list, it's a meta director. That's how the game's played. So we're going to assume all of the groups are strongly deactivating. Yeah, so the meta directors are on this list below the halides in terms of speed. The meta directors shut down the ring and deactivate it. It puts a stop to Friedel-Crafts reactions. It makes the other 6 reactions very, very slow. Why? Because they're the opposite. The OrthoPara Directing group have electron donating groups, usually because there's a lone pair next to the ring. The lone pair can sneak in a ring, pretend it's some pi electrons. Oh, I may have misspoke. This lone pair can't count as a Huckel number, doesn't count as a pi bond. But nature says, you know what, have a lone pair so close by, excites these pi electrons, makes them react faster. So that's why this is an OrthoPara Directing group, strongly activating group. Okay, if you don't have a lone pair, instead you have an atom with a slight positive charge, or maybe a full positive charge, that's going to shut down or deactivate the ring. We say such groups with positive charges on the atom attached to the ring are electron withdrawing. Do I have any examples down here? Nope, just blank space for examples. Okay, so here's a list of some meta directors. Meta directing, strongly deactivating groups. We said in the previous video about the limitations of Friedel-Crafts reactions, we said the nitro group was a deactivating group. Why? Well, let's draw out the Lewis dot structure of the nitro group. There's a plus charge on the atom next to the ring. So these pi electrons, if you do the Br2 or any of the reactions, it's going to happen very slowly. If I would have picked Friedel-Crafts, it wouldn't work at all. But remember, these reagents say what goes on the ring. And these reagents say, well, let's make the electrophile Br plus. And in the first step, we need one of these pi bonds to grab that. Well, this pi bond is saying, we're electrons, we're attracted to the positive charge. Which one should we go after? This nitrogen's closer. So it's naturally inclined to go this way and just hang out here. It's part of the molecule. And it slows down its reactivity. Yeah. So if you have an atom, you can't see it now, put it back in there. If an atom attached to a ring has a plus or a slight positive charge, it's going to make it a meta director, strongly deactivating group. I think we had an example where we said, what if you had a ketone on the benzene ring? Yeah, ketones are deactivating too. They're meta directors that deactivate. Why? Because oxygen is more electronegative than carbon. And whoa, now the atom attached to the ring has a slight positive charge. So any carbonyl, CO bond O group on benzene is going to be a meta director. So aldehyde, ketone, carboxylic acid, an acid chloride. That's kind of interesting. Yeah, so Friedel-Crafts acylation reaction. What's the product? It's where this ring, and only this ring, reacts with the reagent to link them together. And if some of you are saying, well, how come this can't react with another molecule like itself? It's because this molecule is strongly deactivating. And this benzene ring reacts slower than this one. In fact, this is so deactivated, it's so slow, it doesn't react. Sorry, that was a fine point. More to the things that you need to know in class. Double bond O next to the benzene ring creates a positive charge on the atom, makes it a strongly deactivating meta director. What are we missing? Anhydrides, anything else with double bond O. Now let me look at my list. I'll confess, I don't have the meta directors memorized, although one of them just jumped to mind before I look at my list. The trifluoromethyl group counts. If you have 2 fluorines or 1 fluorine on this carbon attached ring, it's still a meta director. It's just a halide group. Well, that's not right. It's just a methyl group. Okay, but if you have 3 fluorines on that carbon, now there's a significant positive charge because of the electronegative fluorines. And now this group, CF3, has a meta-directing, strongly deactivating group. And then the sulfonic acid group, I guess I do have some of these memorized. This sulfur has a whole bunch of oxygens attached to it. Slight positive charge there. That's a deactivating group. What else have you seen? Nitro. No, I already got nitro. Now I need my list. What else we got? Oh, nitrile. Come back. Remember the nitrile group? Cyanide group? Yeah, carbon nitrogen triple bonds is the nitrile group. Nitrogen is more electronegative than carbon. So slight negative charge on the atom next to the ring. What else do we have? Oh, this unfortunately is confusing the students, and I get it. Amides. Wait, Dennis, no carbons halides. The second N stands for amides. It depends on how the amide is connected. So if you have the double bond, carbon-oxygen double bond group attached to the benzene ring, oxygen and nitrogen is more electronegative than this carbon. The atom attached to the ring is now positive. But if you connect the nitrogen to the benzene ring, now you have a lone pair next to the ring. This type of amide is activating, no carbons halides, OrthoPara directing. But the other amide I just drew right here, the double bond O group attached to the ring, that's a meta director. So again, biggest point to remember is an atom attached to the ring with a lone pair, OrthoPara directing, activating, an atom attached to the benzene ring with a slight positive charge, meta directing, deactivating. Cool, and I think I got them all. No, I didn't. I'm looking at the most common ones you see, and I think there's 1 or 2 in the homework that'll just ask you to make a prediction. But if it's not on this list, I'm not going to put it on the test. So this is the last one that can be on the list, and that's the quaternary amine. So if you have 4 bonds of nitrogen, hey, now that nitrogen has a positive charge. And what do we say about positive charges next to a benzene ring? Makes them meta directors. So I think we actually saw that when we're talking about limitations. Here we go. So we said aromatic amines don't do Friedel-Crafts because the amine will react with the catalyst, and then if the catalyst is all used up, can't do Friedel-Crafts. Some people thought, well, let's just throw an excess of catalyst. So what if some of the catalyst gets eaten up? Oh, but it's so much. It still doesn't react because now, after the amine reacted with the catalyst, it's a meta director. It's strongly deactivating, and then limitation number 3 kicks in. Yeah, so now this ring still won't react, even if you still have extra catalyst. Dang it, chemistry. But at least there's some logic behind it. Okay, what else do we need to do? We got our meta directors. You can take a screenshot if you want to start memorizing everything. Again, I don't advocate that. It's good to see some examples to help you recognize things. Those are the most common meta directors. I'll limit myself to this list on exams. This is the most common set of OrthoPara directing groups. I'll limit myself to these types on the exam. But I advocate memorizing no carbons halides, amines alcohols, amides ethers, alkyl, phenyl rings, and halides. And anything that's not on the list, meta director, strongly deactivating. Okay, let's do some examples. How does this all play out? Okay, so the way it works on exams is usually in the question asks you to predict products. So let's do a few reactions where we'll predict some products. Where's my list? There it is. Let's start with this molecule. What's the name of this one? Phenol. The alcohol group on benzene is one of those special names. And I don't care. We can do anything on it. This doesn't suffer any of the Friedel-Crafts reactions. We could do a Friedel-Crafts reaction, so why don't we do that? But you could do any of them. Nitration, put a halide on there, sulfonic acid group, whatever. Okay, how's this work? Predict the products. Okay, the reagents say what? What's going to go on the ring? And that's a CH3 group, right? Specifically speaking, in the optional first step of the mechanism, aluminum chloride rips a chlorine off and makes a carbocation out of the rest of the alkyl group, primary. Ooh, check to see if it rearranges. No, no carbons to rearrange to. Okay, reagents say what goes on the ring. The group on the ring says where. Okay, cool. I had some students talk about sort of like King Arthur and the Round Table. I thought it was a good story, a good analogy. Think of the benzene ring as a table with 6 chairs. And you got a group sitting at the table. It's a dinner party, it's a big restaurant, and this guy's waiting for some friends to come along. You got to know who's the most friendliest group sitting at benzene. It's this list. No carbons, halides. The alcohol and the amines are the partiers. Amides and ethers, yeah, come on over, join me. Alkyl groups, phenol groups, they like having a good time. Halides a little grumpy, but they'll tolerate you. Meta directors don't want anything to do with you. So there you go. Why does that help? This is how the game's played. Okay, reagents say what? Methyl. Directing group says where and how fast. Alcohol, where's that? No carbons, halides. The first no is amines and alcohol. Ooh, this is an alcohol. This is one of the strongest activating groups. This is a lively group. The alcohol's sitting at the table, and across the room sees his friend Methyl. Hey, Methyl, come on over. Have a seat next to me, buddy. Or take the head of the table. Go sit para. Whatever you prefer. Sit right next to me, Ortho. Or go take the head of the table. Your choice. So sometimes the methyl group says, okay, buddy, I'll sit right next to you. And sometimes they'll say, okay, I'm gonna take the head of the table. I'll sit over here. So the OrthoPara directors generate both products. It's hard to know which one's in excess. We don't have that theory yet, but we'll always draw both of them. There you go. Always, gosh, you gotta be careful in chemistry. There's always exceptions. The exception will be if there's another group sitting at that table already. Yeah, if there's already another place taken, remember these reactions only take out hydrogen. So that'll be the exception. If someone's sitting para, you won't get the para product. If someone's sitting ortho, you don't get the ortho product. And if that's not, and then there's 2 ortho products here, but if you name them, they have the same exact name because they're the same exact molecule. So save yourself some time. You don't have to draw both. These 2 are the same. I think that's all I wanted to say. Lost my train of thought there. Oh, I know what I was going to say. We'll do another video dealing with what happens if there's more than one group at the table, more than one directing group. For now, we'll just do a single directing group, right? One step at a time. I think we're good here. Let's try another example. Let's put benzoic acid on the ring. So what's the name of this molecule? Benzoic acid. Carboxylic acid on benzene. Let's do nitration. Whatever. I shouldn't do nitration. Sorry, that's going to confuse a couple concepts. Let's keep it the same. But it could have been. We could do that next if you like. Let's do the same reaction. Because what you pick says what goes on the ring. What's on the ring says where and how fast. Okay, so King Arthur and the round table, carboxylic acid sitting at the table. So you want to talk to anybody? I don't know. What kind of OrthoPara Directing group is it? No carbons, halides. Oh, there's a carbon here. No. Alkyl group's phenyl. So no. Amine, alcohol. No, that's not what we have here. That's not an alcohol. No. Amides, ethers. No, we don't have that. Alkyl groups? No. Another benzene? No. Halide? No. Not on the list. It's a meta director. Super grumpy. An introvert. I don't know about introvert. Maybe I shouldn't say that. Grumpy. Doesn't want to be more, kind of foul mood. Doesn't want any company. Methyl comes into the crowded room, says, looks like there's the only table. There's only one person sitting there. Walks up. Hey, mind if I sit with you? Carboxylic acid just goes. No, don't sit next to me. Don't dare take the head of the table either. He's grumpy. So the only place left is this sorry, on the product side, on the reactant side, sorry. If you don't take the head of the table, because the grumpy carboxylic acid group says, don't take the seat of honor, then you gotta go methyl. And it's the same as the other methyl. You have to go meta, which is the same whether you pick this methyl, meta group, or the other one. These two are the same molecules, right, if you name them? So yes, well, from the point of view of the carboxylic acid, go meta to it. Those are the two possibilities. And in this case, you generate the same molecule, so there's only one molecule, that's me. Nice. Okay, what else do we got? A couple more examples. What about the methyl group? And let's put an iodine on there. What was their catalyst? Yeah, CuCl2. Okay, let's predict the products here. What's going to go on the ring? An iodide. I know, the electrophiles are I+, but iodide's going to head the ring. Where's it going to go? Methyl says where it goes. What kind of directing group is methyl? A meta director? No. Carbons. Halide. Methyl group it's no carbons, then halides. And benzene is right here. So if you want to know how fast, this molecule reacts a little faster than benzene. Carbons, such as a methyl group, are weakly activating. Speeds up the reaction a little bit. More importantly, these are OrthoPara directors. So methyl says, hey, iodide, you want to sit next to me? Or if you want, you can sit at the table. It's kind of a weak deactivator, not too loud, but still kind of polite. Come on over, sit with me. How you been doing? Okay, so iodide then decides, well, maybe I'll come sit next to you. Yeah, hey, buddy, what you up to? And sometimes say, oh, wow, you give me the head table. Thank you. I'll sit up here, opposite you. And those are your two products, ortho and para. And again, if you put the iodine this side, same molecule as this one. What else we got? Two more. Yes, two more. Keep us on our toes. Okay, so. I have to decide what I want. Yeah. F theta BF4. BF. F. Why did my pen write H? There we go. Okay. What goes on a ring? Fluorine. Where does it go? The amide decides. Darn it. Amides in no carbons, halides. It's also a part of the meta directors. Which one is it? This benzene ring is connected to the carbon, which is less electronegative than oxygen. Nitrogen has slight positive charge. This form of the amide is a meta director. It's cranky. Doesn't want any guess, but hey, fluorine, if you have to sit anywhere, go meta to me. Okay, fine. Be that way. Sit meta next to you. Too bad there's not another table in the house. Okay. There we go. So we get this product and we get the other one, happens to be the same. Where the fluorine's at the bottom of the ring. That still has the same name. And we won't have to name that one. When we get to amides, we'll learn how to do it. We haven't seen the amide functional group. Talked about how to name those yet. Last one, I think, yes. Toughest of the bunch. Here we go. I don't know. What haven't I done yet? Sulfuric acid group. I don't want to do that one. How about chlorine? Pause it if you like. This is tricky, right? Because there's two tables. They're joined together. There's two benzene rings. So does sometimes chlorine go on the right table? From the right benzene ring? Sometimes they go on the left. Is it 50-50? Does it prefer one or the other? Directing groups. That'll tell us. It's all about speed of reaction. Okay, so the way you got to think of it is that this is like, what if you had this molecule where, well, let's focus on this table, and we have a benzene ring sitting at the table. What kind of directing group is a benzene ring? No carbons halide. It's like another methyl group. So right here, alkyl groups and phenyl rings are both weakly activating. So if you had a methyl group, it'd speed up the reaction just like another benzene ring. Weakly activates it, makes it go a little bit faster than straight benzene. At the same time, these reagents could choose to go on this ring. And so what's that like? Well, at this table, there's a benzene ring sitting here. Hey, on the other side of the benzene ring, there's a nitro group. That's too far away to matter. Who is sitting at the table? What is the atom attached to the benzene ring? It's a benzene ring. And that's like a methyl group. It's a weak activator. Okay, and now, a little preview of our next video. What happens if there's more than one directing group? They kind of add up, right? So you got someone cranky at this table and someone who's kind of friendly, weakly activating, and their twin is sitting alone at another table, kind of friendly. Which table would you prefer to sit at? Because these two are identical twins. You'll have a nice conversation with either one of them. They're the same. I know that's kind of not fair. I know identical twins in reality are different, but let's simplify it and say that they're exactly the same. You want to sit at a table with the twin with a grouchy person, or the table without one? Yeah, without one. I also had some other students. We'll explain this in the next video too. Had some students play D&D, Dungeons and Dragons, and they said, "Oh, this is sort of like having some armor on. You have a +1 shield, but you're wearing a cursed ring. So you get a +1 on hit damage with this methyl, and you get a -1 on the cursed ring. A -1 and a +1 cancel out. Okay, make the nitro group a -2 in this game. And again, we'll go over this. That's total preview of our next video. But no carbons halides, amines, alcohols are the most activating. Amides, ethers, next activating, just activating. Carbons, weakly activating. Right here's where benzene is. The halides are weakly deactivating. The meta-directors are strongly deactivating. So if you have a weak activator, it's like +1 faster. An amide or an ether is +2. Strong activator, amine, alcohol, +3. Having a halide slows it down, but at least it's still OrthoPara directing. These are all OrthoPara directing. but the meta director is strongly deactivating. That's like a -2. Okay, so I hope you get the sense that, hey, this table is more deactivated than this one. This table is more deactivated than this one. This is the table that reacts. Sorry, this is the benzene ring that's faster at reacting than this one. So that's your major product. Yay, directing group. So we understand that. We can solve this complicated molecule. You take this molecule in the lab, and what it does is says, hey, this ring is more activated than the middle ring. This ring is more activated. Well, how is it activated? It's got a benzene ring on it, just as if it had a methyl group. So methyl, hey, what do you want the incoming chlorine to do? Well, go ortho to myself or go para. And that's what this molecule says. This benzene ring directs this benzene ring to say, hey, incoming chlorine, go ortho to myself or go para. So let's copy the starting material. And then we said sometimes it's going to go ortho to itself. And I know that looks like it is crowding, but this ring can spin 90 degrees. So this hydrogen doesn't have to bump into the chlorine. So it can still go there. And I'll draw it down here because it is kind of a wide molecule. Sometimes the chlorine goes para. So para to this benzene ring would be over here. Those are your two products. Draw them both. You get full credit on the exam. All righty. Have a try practicing in the homework. Post some questions on the discussion board. Let's just talk it out. And we can get this. Cool. Hang in there, and I'll see you in the next video.